Dear viewers, I welcome you, and today we will cover the part 2 of the statistical process control. The part 1 of the statistical process control we have already covered, and in the part 1 of this statistical process control we have covered the importance of the quality. We also had a discussion regarding the historical perspective of the quality along with the various definitions starting from the traditional to the modern definition of the quality. In this part, that is the part 2 of the statistical process control, we will cover the following topics, that is the concept of variations, reasons of variations, causes of variations, and the concepts of SPC, that is the statistical process control, and the concept of SQC, statistical quality control. In the part 1, I had finished my lecture on this particular definition, that is the modern definition of the quality, and we mentioned the quality is inversely proportional to the variability. The entire lecture I will start to build up a theme regarding the variability to understand all the concepts of the variability. Now, just an example to build up the concepts of variability, I have written some points that have you ever shot a rifle or played darts. In both the games, we have the target and we play darts on this target. These are the just two persons, Ram and the Arjun. They basically played the darts on these two targets, and the output of the Ram and the output of the Arjun has been shown by the black bullets. These are the black bullets, that is the output of the Ram, and these black bullets basically the output of the Arjun. Now, question arises, who is the better shot? So, when we think that who is the better shot, first we need to understand what we are going to measure. If we see the Arjun's points, that all the bullets or all the darts right here, they are just close enough to each other and approximately coming to the same point. And as far as Ram is concerned, it is distributed and touching one circle and another circle and the third circle. Now, the question is that whether we are going to take the decision with respect to the consistency or with respect to the total evaluation. So, the question again here is the who is the better shot. So, before we decide that who is the better shot, let us see that what we should do in our processes. So, whenever we do have any measurement of the any characteristics of the process, we should know that what we are going to measure. Suppose there is some shaft that you are turning on a lathe. Now, the question is whether you are measuring the diameter of the shaft, or you are measuring the eccentricity of the shaft, or you are measuring the surface roughness of the shaft. So, first we need to be very clear that what we are going to measure in our processes. Second, the question is why do these measures matter? Means what is the importance of all these measurement? The third question is, are those measures consistently the same? Means when we are saying the measures consistently the same, this means whether the equipment or the measurement tools we are using the same, or the equipments or the tools are calibrated, or the method that is being used to measure is same, or the operator is using the same method consistently first time and the every time. Then when we say that are those measures consistently the same, if yes, good, if not, then we should know why not, that why these measurements are not coming the same. So, before we decide, as I have given the example that Ram and Arjun, they have played the dart game. So, before we say that who is the better shot, we should know what we are going to measure. So, depending upon the measurement that we are doing, we should take the decision. Let us see, because in that dart game two possible measurements was there. One was that the total count, the total number. Second is the consistency. So, when we say consistency means we are talking about the variability, and when we are talking about variability we need to define what variability is. Suppose we define variability as the deviation. Deviation means distance between observations and the mean value or the average value. This is the output of the RAM as I have shown you. In addition to the output in this slide, you will see that I have given the numbers, that to the different output the different numbers are there 8, 7, 10, 8, 9 depending upon where the short is there. So, if you see in this table that there are 5 observations and the average of these 5 observation is 8.4, and if we define the variability as the deviation, this means the observation minus the average value, 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 observation minus the average value. And if you see that first and second, these two observations, the observations are higher than the average value, and in the last 3 observations it is less than. That is why the negative sign is here. So, this figure that represents the sum of the deviations of all the 5 observations. So, this is equal to 0.0. So, when we say the variability of RAM in terms of the deviation from the mean, that is 0.0. Let us see what happens for the deviation with respect to the Arjun. The Arjun same. So, he has the output at 5 output here or 5 observations here, and all these observations are just at approximately near the 1 or the second circle, but none of the observation is at the center or the next circle. So, depending upon his output, the marking scheme is different, because if he marks just in the inner circle, the marks was 10. So, his marks are less. So, let us see the deviation of the Arjun with respect to the observation. So, these are the 5 observation, this gives the average value, that is 6.6, and the next column shows that observation minus the mean value. So, all these 5 observation we have calculated the deviation, that is observation minus the mean value, and the last 2 observations, if you see, the observations are less than the average value, and that is why the negative sign is here, and the total observation, the sum of the deviation, means this sum of the deviation is algebraic sum of the deviation, and that is coming 0.0. So, what is the difference? Ram has the different observations, Arjun has the different observations, and the deviation is coming same. So, this shows that deviation is not the right way to distinguish between the output of the Ram and Arjun. Let us see, we define the variability in another way. Now, we define the variability as a variance. What the variance is? Everybody must be knowing that it is average distance between observations and the mean squared. Again, we will calculate the variance with respect to this definition. These are the same observations of the Ram and Arjun. The observations have been written here 10, 9, 8, 8 and 7. The average we have already calculated, it is coming as 8.4. These are the deviations. 10 minus 8.4 means observation minus the mean. So, all the deviations from the mean values have been calculated, and since we are calculating variance, this is the average distance between observation and the mean squared. So, these are the deviations from observation and the mean, and in the next column we will square all these deviations, that is 1.6 into 1.6 2.56, 0.6 into 0.6 0.36, means all these standard deviations square deviations we are calculating, that is the square of these, and this figure tells us the summation of these things. So, this 1.0 represents the variance of the output of the RAM with respect to the dart game. So, let us see for the Arjun. These are the observations 7, 6, 7, 7 and 6 for the Arjun, and observations have been listed here. The average value is 6.6 that we have already calculated. The deviations, that deviation means that we have already defined observation minus the mean. So, these are the deviations of all the observations, and the next column shows the square of these deviations. So, the square of all these deviations have been given, and the total comes, that is 0.24. This is the variance. Now, if you remember, the variance of RAM was 1.0 and the variance of Arjun is coming as 0.24. So, if we define the variability with respect to the variance, we can say that variance of Arjun is much less than the variance of RAM, whereas the deviation of Arjun as well as the RAM was same 0.0. So, if we define that the decision we have to take based upon the variability, and we define the variability with respect to the variance, and we say who is the better shot, we can say that Arjun is the better shot with respect to the consistency or variance of the output of the results. Let us define the variability again. We are defining the variability with respect to the standard deviation, and standard deviation is what? It is the square root of the variance. So, the variance of RAM was 1, Arjun was 0.24 and the standard deviation is 1 and 0.489. So, even with respect to the standard deviation also, that Arjun is showing the sigma. Standard deviation is represented by the symbol sigma. That sigma value of Arjun is much less than the sigma value of the RAM. So, this shows that Arjun is more consistent in the dart game, although the total number of points may be less, but the consistency wise he is the better one. Now, the question arises that, but what good is a standard deviation, because we are talking about standard deviation. So, how come the standard deviation is good enough to represent the output of a person or output of a process? Let us see what good standard deviation in the next slides. This is a normal distribution curve, and the most of the observation that they follow the bell shape, means the word tends to be bell shaped. If you are just randomly and unbiased way taking the observations will follow the bell shaped curve or the normal distribution curve, means most outcomes occur in the middle. In this normal distribution, that most of the outcomes that are in the middle, fewer outcomes comes in the tails, something in upper side, something in lower side, means some outcomes come in this area. There are some very rare outcomes are there. It says even very rare outcomes are possible, probability is greater than 0, means it goes beyond that middle point in positive side as well as in the negative side. When I said that most of the outcomes tends to be bell shaped, this means even outcomes that are equally likely, like the dice, when you add them up become bell shaped, because a dice has the 6 face 1, 2, 3, 4, 5, 6, and if you just throw the dice, that what is the probability of coming a particular face is, we can calculate, it is 1 by 6. So, if I say that the probability of number 1 coming is 1 by 6, the equal probabilities for the number 2, that is 1 by 6, equal probabilities for the number 3. And if we plot this probability, it will, because every dice is having a single same probability, the curve will be a straight line. But if you throw 2 dice, then the first one will have 1 by 36, another will have 2 by 36. So, like that the total probability will keep on increasing, and that if you plot all these points, all the probabilities of throwing 2 dice, that if I throw the 2 dice, what is the probability of coming the sum equal to 2, what is the probability of sum coming equal to 3. So, if we plot all these probabilities, and same case is true for the when we are throwing 3 dice simultaneously, then we can find out what is the probability of starting from the 3 to 18, that if we plot all these points basically follows the approximately follows the normal distribution. And this normal distribution graph we have already seen, and I mentioned that most of the outcomes that come in the range in the middle area, that is approximately 68% of the area is covered in the middle area, and this is nothing but this is a mean value, means plus 1 sigma minus 1 sigma, means the total area, if we say numerical area 2 sigma area, basically plus 1 sigma and minus 1 sigma, that covers basically around 68%. If we go 1 sigma further here and 1 sigma further here, this total area basically of this curve is 95%, mu plus 2 sigma and mu minus 2 sigma. And if we go further 1 more sigma, that is mu plus 3 sigma and mu minus 3 sigma. This covers 99.7% of the total area of the output, and it says add up about 30 or most things and you start to be normal. Just add anything if they are random and independent, and you will find the things start to be normal. Normal distributions are divided up to 3 standard deviations on each side of the mean, that I mentioned, that this is 1 sigma, further 1 sigma and further 1 sigma. So, on each side means this is mean plus 3 sigma, mean minus 3 sigma. Once we know that this is in most of the outcomes that are random and independent, they follow the normal distribution, and we also know that we can divide up the normal distribution into 3 parts, plus 1, plus 2 and plus 3 sigma on one side, and similarly minus 1, minus 2, minus 3 sigma on the other side, that the entire area, that means 99.7% of the observations cover in mu plus minus 3 sigma. And once we know that, we know a lot about what is going on, and that the answer of our question that we asked what good standard deviation is, and we say that this is what a standard deviation is good for. Means once we have the understanding of sigma, we can find out where the observation lies, whether it is in the middle area plus 1 sigma, 2 sigma, 3 sigma or beyond. If it is beyond, it means it is out of the control. So, this is how we are basically understanding the concept of sigma through the variability. Now, question comes that if you remember that in the case of the RAM, that there are different output starting from the middle observation to the second observation, or to the first circle to the second circle or to the last circle, then certainly there is some reasons of the variations. And earlier as I mentioned that when we are going to for the measurement of a process, we need to check our instrument, that our instrument should be calibrated and it should provide the observation or the measurement consistently. Also the method should be standardized, whatever the method we use to measure the processes, that method should be used consistently, and the operator should be skilled enough so that whatever he is measuring, the way he is measuring, the procedure he is following, that he should use the procedure first time right and every time right. So, but still I mentioned in my first part that there are inherent causes of variation, and let us find out what are the reasons, potential reasons of the variation. The very first reason of the variation is the operator himself, that sometime there is a not proper training to the operator, sometime not proper training for the supervision, and sometime the operator is not using the right technique. Sometime he used the one method, sometime he used another method. So, that basically is that he is not aware of the right technique to measure. There is another reason that the method, that procedures are not standardized. There is setup change, the temperature, and maybe some other conditions, ambience condition that changes from time to time. Say for example, if you take the measurement in any foundry shop regarding the temperature of the molten material in the morning and in the evening, that because of the temperature range, that because in the morning the temperature in the winter season varies from morning to evening. So, that the effect of that ambient temperature comes. So, this may become the reason of the variation. If you have measurement in the morning, if you have measurement in the night, there is a variation in the thing. The variation may be possible with respect to the material, the moisture content, blending, contamination. Sometime what happens when in a manufacturing concern or in a manufacturing organization, sometime the material is coming from one vendor, sometime the material is coming from another vendor. If and there is a possibility that whatever the material is coming from one vendor, the constituent, the characteristics, the properties may slightly vary from vendor to vendor. So, this may become the reasons of the variation. The machine's conditions, inherent precision, sometime because of the usage, the wear and tear happens in the machine, and because of the wear and tear in the machine, there may be some chatter, some vibrations that occurs in the machine. Finally, the management, poor process management and poor system. Sometime what happens if we are having a product or a product design or product characteristics, and we have to develop a tolerance of plus minus 0.001, means up to the 3 place after the decimal. But if the machines that are with that the manufacturing section is having, the machines are not capable to produce that tolerances, then every time whatever efforts we put in, we will not get the right product. So, then this type of cause is basically that occurs because of the process management. You need to basically involve the management, and the management has to look after that. If the machines are not there, whatever effort and whatever the pressure we put on, we will not be in a position to produce the right product. Sometime it happens as a part of the process management that we are not treating the next process in the line as an internal customer. If something wrong happens in the first operation, that mistake basically keeps on adding up in the further operations. So, every time we should consider the next operation in the line as a customer. So, that now whatever we deliver, means whatever we deliver within our organization, that delivery should be 100% right. So, that the things or the things may not get further worsen up. So, these are the potential reasons of variations. I am just again highlighting the points. The reasons may be for operator, the reason of variation may be the method, reason of variation may be the material, reason of variation may be the machine, and the reasons of variation may be poor process management or the management. The causes of variations. There are two causes of variation. One is the common causes, also known as chance causes or inherent causes. The another second one is the assignable causes. This causes is also known as the special causes. Let us see the first type of cause, that is the common causes, also known as I mentioned, known as the inherent causes. That basically common causes, when we remove such causes, we improve the system. So, whenever we have to bring the improvement in the system, we need to control the common causes. What are the common causes? This is because of the variation inherent in the process. That is why I mentioned that these common causes are also called inherent causes. These causes can be eliminated only through improvement in the system. As I have already given you the example, that if you have the machine and that machine cannot produce the tolerances required by the designer, then there is no way out. You have to have the better machines that can cater or that can take care of those tolerances that the designer is looking forward. The second type of causes is the assignable causes, and these assignable causes, if we remove, we can control the process. The common causes, if we remove the common causes, this the improvement in the system occurs, and if we remove the assignable causes or the special causes, the control of the process occurs, or we can say we can have the stable process. This happens because of the variation due to the identifiable factor. As one factor I mentioned, that if you go for a casting in the morning and in the afternoon or in the evening in the winter season, then the temperature difference has the effect. So, whenever we see that if we combine the items of morning session and evening session, it is clearly visible that these are the variation, and we can find out what is the special reason for this, and if we can remove that special reason, the process becomes stable or process becomes in control. It can be modified through operator or management action. We can identify, we can look back, if we go to the history, we can find out what happened to that particular product. Sometime we are using the wrong die, that may be one special reason. Sometime when you are setting the product on a machine, the possibility that tool may fall down or the workpiece may fall down. So, that are the special reasons. So, whenever we find that process is not coming in control or the measurements are not coming in control, there is some special reason, and if we remove that special reason, means we are controlling the process, or we are controlling the process in such a way that it becomes a stable process or a process in a state of statistical control. It may exhibit a pattern. Sometime if we are using a tool to turn a particular component on a lathe machine, and when the tool gets blunt, the next part will have the higher dimension. Once the tool is wearing up or from one part to the another part, so because of this what happens, the trend that we are getting, it is an increasing trend. Every next dimension if we measure is higher than the previous one. So, this whenever we find such reasons, we say that there is some special reason, that is why it is happening, and we need to focus ourselves to remove such causes. Example, as I mentioned earlier also, example of special causes include wrong tool, wrong production method, improper raw material, operator skills, wrong die, etc. We can, there is a possibility, as one example earlier mentioned, that you are using the material is coming from two different sources, and if we combine the data of these two different sources, then certainly the variation is bound to come. So, these are the possible reasons, and but important part in the assignable reason is that these are the special one, and if we remove these causes, we can make our process stable in nature. And statistical process control uses samples to identify that assignable causes have occurred, that already I have mentioned. What the statistical process control is? The underlying concept of the statistical process control is based on a comparison of what is happening today with what happened previously. Means we compare the output of the processes with respect to the output that when the process was in a state of statistical control. So, what we try to do, initially we go for the manufacturing or we go for the measurement of a processes, and we try to find out that whether the process is in control or not, and through the removal of the special reason or through the removal of assignable reason, we bring back the process in a state of statistical control. Once it is in a state of statistical control, we fix up the upper and lower limits, and then we keep manufacturing the things or providing the services in the operations. And later on, when the next products that we are manufacturing, we compare the measurement of the next product with respect to the mean value or the upper and lower limits of the process. So, this is basically the basic concept of the SPC is that we check the what is happening today with what happened previously, and we go for the comparison. If what is happening today is exactly or minutely different from the earlier, means we are still in a state of control. we take a snapshot of how the process typically performs, or we build a model of how we think the process will perform and calculate control limits for the expected measurement of the output of the process. This already I mentioned that we, from the earlier observations or earlier calculations or earlier model that we build, we basically calculate the limits, control limits. So, once the control limits or the limits have been stabilized, then we leave the process alone, because now we understand that process is in a state of statistical control or a stable process. Then whatever the next production we do, we keep on checking whether the next observation or the next characteristic is coming within the control limits or not. So, after taking the snapshot of the model or understanding the process and deciding about the control limits, we collect data from the process and compare the data to the control limits. The majority of the measurements should fall within the control limits. Measurements that fall outside the control limits are examined to see if they belong to the same population as our initial snapshot or the model. The next concept is the statistical quality control. This is entirely different than the SPC. Here in statistical quality control, the purpose or the basic thing is to ensure in a cost efficient manner that the product shipped to the customer meets their specification. Means this is more on the inspection what we have done earlier. Inspecting every product is costly and inefficient, but consequences of shipping non-conforming product can be significant in terms of customer dissatisfaction. If you are sending the right product to the customer, customer will come back to you. If the product is not right, not meeting the specification, not meeting the performance, your product will come back. So, if you are not producing the right products, not delivering the right services, means you are losing the goodwill. This already I mentioned earlier when we defined the quality and the concept of the quality. So, the statistical quality control, it is a process that ensures, or it is a process of inspecting enough product from the given lots to ensure a specified quality level. So, this SQC basically ensures that the sampling process, or that whatever the outgoing quality is, that outgoing quality should be sufficient enough that the production is consistent, or the finished products production is consistent, and the right product is being delivered to the customer and customer is satisfied with the product. The tools and the techniques of the statistical process control are, there are many ways to implement the process control, but the key monitoring and investigating tools include the histograms, run charts, Pareto charts, cause and effect diagrams, flow diagram, scatter diagram and the control charts. These 7 tools are also known as the 7 quality control tools. Sometime it is they are also known as the 7 basic quality control tools. Let us discuss these tools in detail. The first tool in this category is the histogram. What is it? A histogram is a bar graph usually used to present the frequency data. How does it work? What we do? We define categories for the data. If we have lot of data available, then we basically define the categories. Say for example, if the data ranges from 10 to 100, then we define the categories, that the data from 10 to 19, 20 to 29, 30 to 39. So, first define the categories, then collect data, sort them into the categories. So, once the data has been sorted down, then we count the data for each category, that is the frequency, that how many numbers, how many data are coming in each category. Then we draw the diagram. Each category finds in place on the x axis. The bars will be as high as the value of the for the category, and if you see that histogram is shown here, that these are the different bars, and this is first category, second, third, fourth, fifth, the categories are mentioned, and the height of the bar basically represents the value of that category, means how many observations are falling in one category. So, if you see this, that it is very clear that maximum number of observations are falling in this category. What is its use? Histogram provides an easy way to evaluate the distribution of data over different categories. How to go for the interpretations of the histogram? The histogram is an effective practical working tool in the early stages of the data analysis. Whenever we need to go for the interpretation of the histogram, we should ask 3 questions. The first question: how well is the histogram centered? The centering of the data provides information on the process aim about some mean or nominal value, means this histogram basically provides where the mean or the target or the average value lies. Second question we need to ask: how wide is the histogram? This wideness of the histogram basically tells you about the variability. Looking at histogram width defines the variability of the process about the aim. Aim is basically your target value or the mean value or the normal value. The third question is: what is the shape of the histogram? As earlier I mentioned that most of the observation follows the normal distribution if the observations has been taken independently and in unbiased way. Remember that the data is expected to form a normal or bell shaped curve. Any significant change or anomaly usually indicates that there is something going on in the process which is causing the quality problem. If anyhow we do not get the normal bell shaped curve, some different shape, this is a clear indication that something is going wrong with the process or with the services that we are providing. Some typical distribution, this is the normal distribution that we have talked about a lot earlier also, that it is depicted by a bell shaped curve, means there is only one peak, that is that too at the center, and then observations are gradually decreasing on both the side of the mean. Most frequent measurements appears at the center of the distribution in the bell shaped curve. Less frequent measurements taper gradually at both the ends of the distribution, that we have talked about, that on both the sides these are the less frequent measurements and they are basically at both the ends of the distribution. Indicates that a process is running normally, means when you get the normal distribution of your data, that clearly indicates that the process is running normally, means there is no special reason, no special causes of variation or no assignable cause is there, only common causes are present, means whatever the variations are there, inherent variations are there, only those variations are present in the data. The another distribution is the bimodal. If you see this figure, that it shows very clearly that there are 2 peaks, means when instead of one peak we get the 2 peaks, that type of distribution is called the bimodal, and distribution appears to have 2 peaks. It may indicate that data from more than one processes are mixed together. So, this happens because of the many reasons. One reason is mentioned here: materials may come from 2 separate vendors, and when we collect the data from the processes, and in the history of the processes the batches are coming from the purchasing section, the material is coming from the purchasing section or from the inventory, there is a possibility that one lot of the material is coming, that is basically belongs to one supplier, and the another lot belongs to the another supplier. If we are combining the data of the material that is coming from 2 different suppliers, there is a great possibility that we will get that this type of distribution that is having the 2 peaks. There is another possibility that the samples may have come from 2 separate machines, means when we are collecting the data, we are collecting the data from 2 separate machines and we are clubbing the values or the observations of these data. There is possibility also that sometime when we collect the data, we never bother about when this material has been or when these observations have been taken. Sometime we club the data of the two different operators. Sometime we club the data of two different operators working in different machines. Sometime we collect the data when the different operators are working in different shifts. So, the question point here is, anytime we collect the data, care should be taken into account that the data should be from the single source and from the same operator, same machine, and all care should be taken into account that the same measurement method in all the data, same tools, same material, and all the properties and characteristics should be same. Only then the data will behave like a normal distribution. The third distribution is the cliff like, and if you see here in the cliff like distribution, that data is decreasing, and this is a clear indication that once the data has been collected, some sorting has been done. The data has been arranged in the descending order. So, this appears to end sharply or abruptly at one end. This indicates possible sorting or inspection of non-conforming parts. What are the limitations? Histogram is a very simple tool we use in our daily life, but still, because simply just seeing the histogram, we know only the centering of the process, we know the spread of the process by just understanding the width of the histogram, and only information we can get that the process is behaving normally, and with that particular average value or the mean value, as well as particular width or particular value of the variability. The limitation of the histogram, that histograms are limited in their use due to the random order in which samples are taken and lack of information about the state of control of the process. So, once we have the data and then when we convert into the categories, we count the frequency, but later on once the histogram is ready, then if we want to know something that what happened to that particular observation, that observation is lost. Only the information we are getting that the data has been arranged in 5 or 10 categories, and that every category has this value. So, the data information is lost. This is one of the limitation. The another limitation is that because samples are gathered without regard to order, the time dependent or time related trends in the process are not captured. Means when the first data has been taken and when the next data is taken. So, this basically the time dependent activities or time dependent trends in the process is not captured, and these are the limitation of the histogram. This lack of information on process control may lead to incorrect conclusions being drawn and hence inappropriate decisions being made, because once we do not know when the data has been collected, we cannot go back to find out from the history records about the product or about the processes, what happened to the process, why the process is not behaving normally. But still, with these consideration in mind, the histogram simplicity of construction and ease of use make it an invaluable tool in the elementary stages of the data analysis. So, this although it has the limitation, but the histogram is very simple tool. Once we do not know anything, once we have collected the data, the very first point is that if we do not know any analysis, first try to develop the histogram. Once the data is converted into the histogram, it gives you some information about the process, that how the process entered, whether the process is behaving normally or not, what is the extent of variability or the deviations among the data is there from the mean value. So, that information we can get from the histogram. The limitation that I mentioned earlier in the histogram, that is basically the time dependent activities are not recorded. We cannot obtain the information with respect to the time regarding the data that we are collecting. This limitation is overcome in this next chart, that is the run chart, and run chart is very common If you see the figure here, that on the one axis we have the time, on the another axis we have the measurement. So, anytime we get the data, we just note down the time and the data. Next we collect note down the time and collect the measurement value. Like that we keep on just noting the time, and at that time what is the measurement value, and we just join the data with the straight line, and the run chart is ready to use. And if you see this data, that this is the run chart, and these data points basically is being joined from the previous data with a line, and we know all the values. If we take the average of all this value, we can draw a horizontal line here. So, once we draw a horizontal line here, that basically tells us the average of all the data. So, average value is also can also be obtained in the run chart, and the minimum value and the maximum value we also know, and once we know the minimum value and the maximum value of all the observation, we can find out what is the range, what is the variability with respect to the range of the process. So, whatever the information we are getting in the histogram, that information we can also get in the run chart, because we can get the mean in the histogram, the mean value we can get from the average of all this data, and the minimum and maximum value we are getting from here. So, the variability or the width of the data we can obtain, but the additional benefit is that we are also getting the time dependent activities, at what time the observation was there. Now, coming to this, what is it? Run charts are representing change in measurement over a sequence of time. How does it work? It is very simple. I earlier mentioned, first gather the data, organize the data, measurement y, that is on the x axis, y axis must be confronted with time or sequence of the event. It is not always necessary that x axis should be time, means the first observation, second observation, third observation, fourth. So, we can write down the order of the observations, then chart the data and go for the interpretation of the data. What is its use? Apart from the information that we get from the histogram, we also get the ordered information. So, the use is determining cyclic events and their average character. Run charts, often known as line graph outside the quality management field, it displays the process performance over time. Upward and downward trends, cycles and large variations may be spotted and investigated further. So, this is the additional benefit apart from the order of the observation, that we can also, this run chart also reveals the trends. Trends may be the increasing trend, decreasing trend, increase in the dimension from one observation to the next. Maybe some repetitive cycles are there, that after every 10 observation the observations values keeps on repeating, and maybe some large variations because of the ambient conditions that can be spotted by investigating, and we can investigate further why this is happening. Also, that I already mentioned, an average line can be added to a run chart to clarify movement of the data away from the average. So, if we know the average value, we can draw a horizontal line, we can find out that how the data is deviating from the mean value. Two ways to misinterpret the run chart. What happens that we conclude that some trend or cycle exists, when in fact we are just seeing the normal process variation, and every process will show some variation. This type of misinterpretation in the quality control field we say the type 1 error, that when everything is behaving normally, means whatever the data we are collecting, it follows the normal distribution, and by chance randomly if you just collect take the one observation, it falls beyond the 3 sigma control limit, then we say that process is not behaving, although the process is behaving right. And sometime just collecting the 7 or 8 or 10 observations, we see that there is some trend or some cycle exists, actually there is no cycle or no trend is existing. So, this is very common misinterpretation of the run chart, that we conclude something about that something wrong is going on, although there is nothing wrong in the process. The other error is sometimes we do not recognize a trend or cycle, although it exists, means process is not behaving right, there are cycles, trend and problems are there in the process, but we are not able to recognize from the run chart. Means sometime what happens, we have very small little information or few observations there, and if we plot 5 or 6 observations, those observations are not sufficient enough to reveal whether there is cycle or trend exists. So, this is the another observation, and we normally say it is type 2 error. When there is a wrong in the process has gone wrong, but we are concluding that process is working fine, that is the type 2 process. So, again I am repeating, type 1 error basically is that when process is in control, everything is there right, but we are concluding that something wrong is there, and another type 2 is that when the things have gone wrong, but still we are concluding that process is behaving correct. So, both of these mistakes are common, but people are generally less aware that they are making the first type and are tampering with a process which is really behaving normally. So, this is very common mistake, and possibilities are there when we just decide or conclude that something is wrong, although the process is behaving normally, we try to correct the process, correct the correct process basically. To avoid such mistakes, use the following rules of thumb for run chart interpretation. The first rule of thumb is that look at the data for a long enough period of time, so that a usual range of variation is evident. Never conclude just by collecting very few data and taking the wrong decision. So, first let the process go and take the sufficient information or sufficient observation, then conclude it. Is the recent data within the usual range of variation? Also have an eye that whatever the data you are obtaining, that is coming in the usual range of the variation. Is there a daily pattern, weekly pattern, monthly pattern or the yearly pattern? So, these are the 3 rules of the thumb rules that you need to ask yourself, and you need to check yourself, that look at the data for a long enough period of time, check is the recent data within the usual range of variation, or the third point is there daily pattern, weekly pattern, monthly pattern or yearly pattern we are looking around. We are finishing the part 2 of statistical process control right at this point, and we will continue the rest of the 7 basic quality control tools in the third part of the statistical process control. Today in this part 2 of the statistical process control, we have learnt about the concept of the variation. We also had talked about the potential reasons of the variation, causes of the variation, and we have also got the conceptual background of SPC, that is the statistical process control, the conceptual background of statistical quality control SQC, and the 7 basic tool, and out of the 7 basic tool we discussed in detail about the histogram as well as the run charts. Thank you viewers.